Today we're going to be looking at solving systems of equations by graphing and substitution. And today's objective is, I can solve a system of equations by graphing and substitution in 2 out of 2 problems. That makes sense. That was our subject for today. So to get started, we're going to get out our pointers. Now I know you don't have a live pointer, you're just watching a video, but you can use your pointer on the video all the same. We're going to determine how many solutions each graph has. So we're going to be asking, is it going to have 1 solution, 0 solutions, or infinite solutions? Let's look at our first one. How many solutions does this graph have? If you said 0, that's correct. These are parallel lines. So the number of solutions is the number of intersections. Since there are no intersections here, that means there will be no solutions. Let's look at the next one. How many solutions for this system of equations? Remember, we have 2 lines. That means we have 2 equations. Did you say 1 solution? Great job. They intersect at 1 point right there, and -2, maybe a little bit more than 1, -1. So there is exactly 1 solution to this system of equations. Let's look at the next one. Did you say 1 solution? That's correct. 1 intersection here. Next problem. Now there are 2 lines here. They're a little bit hard to see. There's a red line and a blue line right over the top of it. How many solutions does this system have? Did you say infinite solutions? Yes, every point along this line is a solution. So there are infinite points. This is going infinitely off in this direction and down in this direction. There are infinite solutions to this system. Next one. How many solutions? There are 0 solutions. That's correct. These are parallel lines. They never intersect, so no solutions. Once again, we have 2 lines here. How many solutions? There are infinite solutions on this one. And this one? 1 solution, you can see it right over here. That was 0 solutions. These are parallel lines going up forever. They're the same distance apart the whole time. They never get closer, they never get further apart. No intersections means no solutions. Great job on all those. Hopefully you're getting the hang of that, figuring out how many solutions based on the graph. So now that we've looked at how to get the solution for systems of equations from a graph, let's work on some algebra. Doesn't everybody love algebra? Isn't this exactly how you want to solve systems of equations? I mean, maybe not. Maybe not everyone loves algebra, especially when we have graphing so handy, right? If we have Desmos available, we can just type those equations in and look at the solution. Why would we ever use algebra? Why would anybody ever use algebra? What reason could we possibly have for using algebra? Well, maybe let's take a look at Desmos. Let's look at an example and see. So here we have a system of equations graphed in Desmos. And let's look at that and say, how many solutions are there to the system? How many solutions would you say? Well, it looks like these probably don't intersect, right? Looks like they're probably parallel, so we'd say 0 solutions. Looks like it's just going to go off forever that way, off forever that way. They'll be the same distance apart. But let's just go on a little journey here. We're going to travel up this graph. We're going to go up some more. And notice I'm not zooming in or out. I'm just traveling up. And look what happened to these 2 lines. What is happening? It looks like they're getting closer together. But if they get closer together, that means we're going to find a solution. They're going to cross at some point. Look at that right there. That's right where they cross. 300, 200. And now that red line is going to go on top. They actually did intersect. Now wait a second. Didn't we say these were parallel? We looked way back at the beginning. Those definitely looked parallel to us. How did they end up intersecting? Well, the answer here is that the slope is very, very slightly different. It's so slight that our eye can't see it. But if we look at the equations, let me open up the equations for you here. Now you can see these are in slope-intercept form. This slope is 199 over 300. This one is 198 over 300. Those are definitely different numbers. We can see that right away with the equation. But it's something that was obscured when looking at the graph because our eye is not as sensitive to very slight deviations in slope. So maybe that's one reason we might want to use algebra, because maybe we can't actually see the difference, or we can't intuit the difference on the graph. So in addition to that, there are other reasons you might want to use algebra. The one we just looked at showed us that graphs can sometimes be misleading. Other reasons, though, you might want a very precise answer. So if we have a graph, we can estimate. We could say, oh, this is pretty close to 5.2. But if we want a very precise number, if we want like a fraction, like 15 over 16, we will want to use algebra to get a very exact number. And the third reason I have up here why we might want to use algebra instead of graphing is, what if we have more than 3 variables? If we have 2 variables, we definitely know how to graph that, right? We just graph it on an x and a y. If we have 3 variables, we're thinking in 3 dimensions now, sort of 3-dimensional space. And there is a way to graph that. It's a little bit hard to visualize. We don't have a lot of tools to do that. We sort of have to think with depth in the paper. We have to sort of be artists to draw that. But what if we have more than 3 variables? We could potentially have like x, y, z, and w. We could have 4 variables in an equation. And then how would we graph that? We don't have a way to visualize that. So this is another reason why we might want to use algebra, because we actually can't graph some equations. But now, all of that being said, all of those reasons we might want to use algebra, the truth of the matter is systems of equations are systems of equations, and they have one particular answer, and no matter what method you use, you should get the same answer. Now, some methods are going to be easier than others in certain situations, but a lot of you are going to think, I just want to use graphs all the time. And I want you to realize that is okay. If you want to use graphs all the time, that is your prerogative, and you can solve these using graphs. You can always pull up Desmos if you want to. The reason we solve with algebra, the reason we go through this is really just to learn the skill. And if you intend to go on with math, if you intend to do higher level math and engineering and things like that, these skills will be very useful for you. But if right now you're just like, I want to solve these with graphs, honestly, there's nothing I can do to stop you. So we will say on quizzes, on tests, solve this by substitution, solve this by elimination. And you may look at that and be like, nah, I'm going to solve it with a graph. And that's okay. If that's how you want to solve it, that's totally okay. If you can solve it any way, that'll make me happy. We are, however, going to look at some methods of solving algebraically, just so you've seen them and just so we have these tools in our tool belt. So solving by substitution is one we're going to look at today. Now, we've done substitution in this class already this year. We've looked at functions, maybe something like this, 3x plus 1. And we'd say x equals 2. Evaluate this at x equals 2. This is a substitution problem because we're going to take this value of x and plug it in everywhere we see x. So it goes in there, and it goes in there. We get f of 2 equals 3 times 2 plus 1. That equals 6 plus 1, which is 7. That is a substitution problem right there. We're going to be doing something very similar today. The only difference now is that instead of one equation, we're going to have two equations. And instead of one variable, we're going to have two variables. So let's take a look at how we do that. Here are our steps over here on the side. Notice we have one step up front where we need to get a variable by itself, so we can do substitution. But beyond that, we'll just substitute and then solve. That's the steps where we just did on the previous slide. We're used to that. And then we need to repeat it. We need to substitute and solve again. That's because we have two variables. So we're just going to repeat this process. So let's see how this works. First step, choose an equation, get a variable by itself. Well, I look over here and I'm like, well, look, there is a y by itself already. So I don't even need to do anything. That's already been done for me. Step number 2 is substitute into the other equation. So I'm going to put a box around everything that is equal to y. All of these things are equal to y. Y is equal to y is equal to y, and up here, we know this is equal to y because there's an equal sign between them. So all of those things are equal to y. So if that's true, if all of those boxes are equal to each other, that means we can put one in place of the other one, and everything should still be true, right? So we could potentially take this box and put it in here. And that's exactly what we're going to do. I'll take this value and put it in this box. We get 2x minus 7 here. And then I bring my negative 10 down. Well, now we just have one equation in one variable. We can solve that. Let's see, well, let's combine like terms. Negative 3 minus 2, or sorry, negative 3 plus positive 2. That'll be negative 1. So negative 1x minus 7 equals negative 10. We're going to add 7 to both sides. We're getting x by itself. These 7's will cancel. We have negative 1x equals negative 10 plus 7 is negative 3. Now I need to divide both sides by negative 1 to get x by itself, because we're multiplying over here. We get x equals negative 3 divided by negative 1. That's going to be positive 3. So then we substituted and solved. That's the steps we just took. Are we done? We got an x equals 3. Are we done here? No, we are not done. We have 2 more steps. We need to substitute again and solve. That's because we have a y value we still need to find. We don't know what the y value is. So I'm going to take this x equals 3, and plug it back in to one of these original equations. I'm just going to choose the first one. Y equals 2 times, I'm going to put in the value of x is 3, minus 7. 2 times 3 minus 7. We can simplify that. That is 6 minus 7, so y is negative 1. Now you might ask, could we have used the other equation? Does it matter which one you choose? Let's try it. Let's just see what happens if we put x in the other equation. Negative 3 times x, which is 3, plus y equals negative 10. Simplify that. Negative 3 times 3 is negative 9, plus y equals negative 10. We'll add 9 to both sides to get y by itself. And look at that, we still get y equals negative 1. So we just showed that it doesn't matter which equation you choose. You could choose either one, and you should get the same answer. Now when we have answers to systems of equations, we're going to write them as ordered pairs, 3, negative 1. Remember, this is also what it would look like if we were looking at the graph, right? This is a point where the lines would intersect. And this is how we write a point. So that is our answer. We finished this out with a substitute step and a solve step. Let's look at another example. All right. Get a variable by itself. Well, do you see a variable by itself over here already? How about this one? This y is the same as this y, which is the same as everything on this other side of the equal sign. All those things in the box are the same. So we're going to take this box and put it in place of this y. Here we go. X plus 2 times this whole box, negative 2x minus 6, and we bring down the equals 0. Once again, now we just have one variable that we just need to combine and solve. So we will distribute here. We get x plus 2 times negative 2x is negative 4x. 2 times negative 6 is negative 12. This equals 0. We'll combine like terms. 1 minus 4 is going to be negative 3x. Bring everything else down. We add 12 to both sides. We're getting x by itself. We have negative 3x equals 12. And our last step here is we will divide by negative 3 to get x by itself. Now, I said last step, but I just meant last step to get x. 12 divided by negative 3 is negative 4. We did this step, we did this step, we did this step. But we still have 2 more steps because we don't have a y yet. We still need to solve for y. So we're going to take this x value, put it back in one of these equations. Let's do this second equation. I like to use the one where the variable was isolated, so let's do that. Y equals negative 2 times, put in the value for x, negative 4, minus 6. Negative 2 times negative 4 is positive 8. And 8 minus 6 is 2. So our answer here is negative 4, 2. Here's one for you to try on your own. Go ahead and pause the video and then come back and see if we get the same answer. All right, so let's start out here. We're going to get a variable by itself. How about this x? Looks like x is already by itself. Things in the box are the same. X is the same thing as x, and x is equal to this stuff over here. So let's take this box and put it in place of that box. 3 times 2y minus 9 plus y equals 8. Now we solve that. Let's distribute. 3 times 2y is 6y. 3 times negative 9 is negative 27. Bring everything else down. We will combine like terms. 6y plus 1y, well, that will be 7y. Bring everything else down. We're getting y by itself, so we need to get rid of the further away term. We're going to add 27 to both sides. 7y equals 8 plus 27 is 35. And our last step to find y is to divide both sides by 7. These 7's will cancel, and 35 divided by 7 is, so we get y equals 5. But we're not done yet. We still have this next step to do, substitute. So we're going to substitute this y into one of these equations. Let's try this first one. Let's do it up here. So we have 3x plus y, but we have a value for y, so we're going to put in 5, and then equals 8. We need to solve for x, so we're going to get rid of the other terms. We're going to subtract 5 from both sides. We get 3x equals 8 minus 5 is 3. And our last step is to divide both sides by 3 to get x by itself. 3 divided by 3 is 1. So it looks like that's our answer. X is 1, y is 5, and we would write that like this. 1, 5. There's our answer. Hopefully that's what you got as well. Or if it's not what you got, you can learn by what you did wrong. We finished the substitute step, we finished the solve step. All right, let's look at one that's a little bit trickier. What is the first thing we need to do in this one? Well, this is trickier because we don't have a variable by itself. We actually have to do this first step now. We have to get a variable by itself. So we need to pick an equation that we can solve, and hopefully it's one we can solve pretty easily to get a variable by itself. So I think this one looks pretty promising. Maybe let's solve that one for x. So if we have x plus y equals 1, and I want to solve for x, I just need to get rid of this other term. So I'm going to subtract y from both sides. We get x equals 1 minus y. Now we have a variable by itself, and we can draw our little boxes. X is by itself. It's the same thing as 1 minus y. All of these x's also represent the same thing. So I should be able to take this value from the box and put it in for that x in the other equation. Let's give that a try. So 1 minus y is what we're going to start with, value in the box, plus 2y equals negative 4. We just brought the rest of that down. Let's combine our like terms, negative 1y plus positive 2y. That's going to be positive 1y. So that'll just be 1 plus 1y is y equals negative 4. Then we will subtract 1 from both sides to get y by itself, and we get y equals negative 5. So we've done this step, we've done that step, we've done this step. We still need to get an x value though, so we're going to substitute this y into one of the original equations. Let's use the first one. So we have x plus y, but our y value is negative 5, and that equals 1. So now I need to get x by itself. To do that, I'm going to add a positive 5. We are adding negative 5. The opposite is to add positive 5. These negative 5s and positive 5s will cancel. We get x equals 1 plus 5 is 6. So our final answer here is 6, negative 5. Finished that one up. Great work. Okay. How about this one? Let's practice on another one. This one doesn't have a variable by itself, so we're going to need to do that again. Looks like maybe this y, that one doesn't have a coefficient, so maybe it would be a good one to solve for. Let's solve for that y. Negative 3x plus y equals negative 3. I'm going to solve for that y. So I just need to get rid of this other term. I add 3x to both sides. Those 3x's will cancel. And we get y equals negative 3 plus 3x. Now we have a variable by itself. We can draw our boxes. Box over here. Let's see, all the y's are boxes. So we should be able to take this box and replace this box. That's the other equation. So that's what we're going to do. We do 6x minus 2 times this whole box, so 2 times that whole box, negative 3 plus 3x. We bring down our equals 6. We need to solve that. We're going to distribute. We get 6x. Negative 2 times negative 3, that's going to be a positive 6. Negative 2 times 3x, that'll be a negative 6x equals 6. But look, when we try to combine like terms, 6 minus 6, that's 0. 0x is 0. So those terms actually just go away. They cancel out and we get 6 equals 6. What does that mean? Question mark, question mark, question mark. What does this mean? 6 equals 6. We didn't get a variable answer. We didn't get an x equals something or y equals something. What does it mean when 6 equals 6? Well, if you'll recall when we looked at graphs, a lot of them had one solution, which is where we get an x and a y value, but there were these other options as well. Sometimes they have infinite solutions where they're both the same line, and sometimes there are 0 solutions where there are no intersections, there's no solutions, parallel lines. So if we get an always true statement, this is one of these other options. Always true is this one right here. They are the same line. There are infinite solutions along that line. Now remember, that doesn't mean every point on the graph is a line. It just means every point is a solution. It just means every point on this line is a solution to the system. So that's what it means when you get a true statement like 6 equals 6. This is infinite solutions. But we have to say which points. So infinite solutions on the line, 6x minus 2y equals 6. Interesting. Okay, so if we get an always true statement for infinite solutions, what do you think we might expect for no solutions? If this is always true for infinite, maybe it's never true for no solutions? Maybe let's try one and see. So here we have a y by itself already. We don't have to do that step. We can put boxes around our y values. We can bring this one down into that y. So we replace this box with that box. We get 2x plus 1/3 times y, so everything in this box, negative 6x plus 9 equals 1. We'll use distribution. We get 2x plus 1/3 times negative 6. That's negative 6 divided by 3, so that sounds like negative 2. And then multiply by x. And then this is 1/3 of 9. 3 divided by 9, that's 3. Oh, I'm sorry, not 3 divided by 9. 9 divided by 3 is 3, equals 1. And look here again, we have 2x minus 2x. Those are going to cancel. 2x minus 2x cancels, and we get 3 equals 1. Now, I don't know about that. I have never seen the 3 that equaled 1. 3 equals 3, not 1. This is never true. This is a nope. So this is an always false statement. 3 is never equal to 1. And this is going to be a false statement for no solutions. This is like 3 equals 1. This is like 6 equals 6. So these are parallel lines, no solutions. So those you might see when you're solving by substitution as well. You might see false statements, which tells you there are no solutions. And that covers everything for today's objective. I can solve a system of equations by graphing and substitution in 2 out of 2 problems.